fully autonomous disaster response is going to be very, very, very hard. Even fully autonomous inspection it will be also very, very hard. So we always imagine a machine will be hooked up to human. Human is going to watch where the robot is going. It's not going to command every single detail, but general high-level command will be done by human. When it comes to like some action, like hand action and manipulation, we believe human is going to take over a lot more. So grab this or use this tool to pry open. A lot of detailed decision making can be very, very hard to be automated. So we are actually also doing a research on balance feedback. So once the robot stands up, either on three leg or two leg, we should be able to perform high force actions, which require quite a bit of balance action, which can be also very complex. So we are not only thinking about just like teleoperating machine in distance and commanding some motions, but also thinking about the balance, the robot, and then the operator should be able to feel the balance. At the same time, you can actually utilize the being able to control the balance to generate more forces. For example, opening door or punching door, you can't just punch door by standing. You have to actually shift your momentum of the body to generate more forces. So we are focusing on the teleoperated teleoperated monkey robot, for example, but with the balance feedback built into the operator side. So eventually, we hope we can develop a machine that can not only search in the disaster situation, also rescue a person out of it. We're not really sure the robot will physically carry the victim or will bring some device that can easily carry a human. So hopefully we can reach that level. But dealing with the human body is actually a lot more difficult than dealing with the objects like doors and walls. But hopefully we can figure it out by the time we reach that level. So Cheetah 3 is designed to operate untethered and being able to carry up to 20 kilograms. But it's, the payload is depending on what you want to do. If you want to travel longer, probably some of those payloads should be shipped to the battery. Or if you want to just operate short and then you want to just carry more heavy stuff for a short period of time, then more weight will shift it to the payload. So the machine is completely untethered. It can operate several hours of walking. Yet when it comes to real disaster situation, I believe we need to have some sort of wired communication, not for power, so that we can actually make sure we have a reliable communication. I can give you an example for disaster situations like Fukushima. If your machine go inside a building, there's no way we can communicate with that machine. So we need some sort of wire. Eventually, I believe we will going to use bulletproof fiber optics, which will be definitely suitable for disaster situation like that. Yeah. So typically the command to the robot in manipulation side is just copying human's motion, but that's typically not enough to give the robot to manipulate things in a complex way. So we can easily add like force feedback on the arm, but that kind of technology is only suitable for a fixated machine. When it comes to machine is mobile, you have to actually care about your balance a lot more. That's actually more crucial than actually feeling the force in the arm. So we're actually focusing on balance feedback. So we want to give some sensation of robot's balance so that the operator can actually sense the situation of the robot in terms of the balance. We can actually react on or plan on to generate more forces or to effectively use this body weight to generate high payload actions. So what we developed in our lab is basically more like a human-like or animal-like actuation. So you can actually you can handle impacts, and that's why we could run, we can jump. If you look at typical industrial actuators, motors, and gears, those are not be able to do that kind of dynamic motions, and very stiff and then mostly position controlled machines. So we were thinking about how can we provide this kind of environment to other people, even my undergrads. And our electric motors and the Cheetahs are very heavy and expensive and dangerous. So we actually developed a scaled down version with a very similar characteristic. It can generate high torque and high speed with also very flexible. So we designed our special module and very cheap price at this point. So we're actually trying to disseminate this very different type of electric motor module, so many students can actually learn this type of more physical interactive robotics very soon. So we're actually at the verge of like disseminating this new technology. We're planning to elect a couple of labs in the United States and then send those modules so that they can do some benchmark test, and then they can give us feedback. And then if that goes well, we're trying to disseminate more so more students have access to this like dynamic and physically interactive actuators. So Mini Cheetah is basically trying to show that capability first, because if you show just actuator in the picture, nobody will understand what it is. So we're actually put together into basically half-size Cheetah and then show the capability to really to inform what how different these actuators are from others. Yeah.